Welcome to Notes 2.3b. We're going to be continuing looking at our real zeros of polynomial functions. So as a reminder, a zero is where it crosses the graph at an x-axis. At the x-axis, right there. That's what we're looking for, some critical values of our graph. So this one says a polynomial function f of x has a factor x minus k if and only if f of k equals 0. So this is a new theorem to us, but this isn't new news. It's basically saying we can take that and that's our 0, right? That's where when we're on our graph it equals 0. That's where if we plug it in, we equal 0 at y. So now it's just wanting us to say, show that x minus 2 and x plus 3 are factors of this. Then find the remaining factors. And so we could use long division or synthetic division. I'm going to go ahead and use synthetic just because it's faster. So we have 2, 7, negative 4, negative 27, and negative 18. If you prefer long division though, more power to you. Continue doing so. And I'm going to start with this 2. So the 0 is the 2. The function was x minus 2, a part of the function. So when we take it out, that's the 2. So it's saying, show that it is a factor. So that means that when we plug it in, we should get 0. And so that means we should have no remainder. So we're going to go ahead and bring this down. 2 times 2 is 4. 7 and 4 makes 11. 11 times 2 is 22. And so we see where we're going here. We're just going straight down. So that's 18. 18 and 2 makes 36. Go straight down. That gives us 9. 9 times 2 is 18. And this gives us 0. We know whatever number here we get as our remainder is the value of that point. So if we get 0, we know that this is a 0. So 2 is a 0. Great. But now it still wants us, so we know when we divided this we could simplify it. 2x cubed, since we started with x to the 4th. We're going to go down a power. This is what we get to. We still have one more 0 that we can plug in. So let's do synthetic division to what we just got here. So this is x plus 3, so we're going to use negative 3 for synthetic, or you could do long. And we're just plugging these values straight in, our coefficients. So we're going to go down. 2 times negative 3 is negative 6. 11 minus 6 is 5. 5 times negative 3 is negative 15. 18 minus 15 is 3. 3 times negative 3 is negative 9. And we get 0, so we know negative 3 is also a 0. Yay. We proved it. And so now what's left here? We have 2x squared plus 5x plus 3. So it says find the remaining factors of f of x. Well, can we factor this? Absolutely. I'm going to use my method. You use whatever method that you want to factor this. I do bottoms up, so multiply the bottom to the end. Factor it. What multiplies to give 6 and adds to give 5? 3 and 2. And then we go back and we divide by what we multiplied by to undo that. So this can't simplify, so we do bottoms up. 2x plus 1. And this one does simplify, and we get 1. So our remaining zeros would be negative 1/2 and negative 1. And we have successfully solved for the zeros of this quadratic. If we wanted to write the complete factorization, we know we have these factors and these factors. So we could rewrite this as x plus 3. And what was our other one? X minus 2. This would be our complete factorization because that has all of the points that were the factors there. Okay, so now we're going to get into the rational zero test. So the rational zero test relates the possible rational zeros of a polynomial. So like in all of these problems, they've given us where the solutions are at. But what if we don't know what the zeros are of a function? Well, we actually have this test here that can help us actually discover what they are. So it says if we have a polynomial that has integer coefficients, so that means we don't have any fractions or decimals in front of our coefficients, only integers, positive or negative numbers, or 0, then every rational zero has the form p over q, where p and q have no common factors other than 1. P is a factor of the constant term a0, and q is a factor of the leading coefficient right there. So our leading coefficient. So this sounds like really confusing. Basically, we're looking at this p over q. So p is the factors of the constant term divided by Q is the factors of the leading coefficient. So we're looking at the factors within our equation to determine the possible rational zeros, to see which ones that we have here. So find the rational zeros of this. Well, let's see. What's our constant term? Our constant term is 1. So what are the factors of 1? 1 and -1. And then the other one is our leading coefficient. In this case, is also what? 1. So the coefficients are 1 and -1. So for our rational zero test, we would write 1 and -1 up here, and 1 and -1 down here. So we're dividing them. 1 divided by 1 is 1. -1 divided by -1 is also 1. 1 divided by -1 is -1. -1 divided by 1 is -1. So our possible rational zeros are only 1 and -1. We can see now if these are true by testing them. So these are our possible rational zeros that we got by setting up this fraction. So let's test them. If we plug in 1, 1 cubed is 1, plus 1 is 2, plus 1 is 3. That is not it's not a real 1, because it didn't work. -1, -1 cubed is -1, plus 1 is -1. So we have -2 plus 1 is -1. So that's also not real. So this polynomial has no real zeros. Because when we plugged them in, we did not get 0. So let's look at another one that maybe will look a little bit different. So this one, let's look at what our constant term is. Our constant term is our number without the variable, is 3. And our leading coefficient is 2. So what are our factors of our constant term? Factors of 3 are 1 and 3, plus or minus, right? +1 and +3, or -1 and -3. Our factors of our leading coefficient of 2 are going to be 1 and 2, right? So now we do the possible rational zero test. So we do the constant term, plus or minus 1, plus or minus 3, over the leading coefficient, plus or minus 1, plus or minus 2. And so now we're going to determine our possible rational zeros by dividing everything out. So we have the choice of 1 over 1. We have the choice of 3 over 1. We have the choice of 1 over 2. And we also have the choice of 3 over 2. So these are all of our possible rational zeros. We could plug these back in to determine which ones would work. So we can say, we could even type it into our calculator and do the table. 2x cubed plus 3x squared minus 8x plus 3. If I go to table, I can type in these values. So if I plug in 1, -1, oh hey, look, at 1, I get 0. So I know 1 is a 0. How many should I have here? Potentially 3, right? I could keep plugging these into my table and see which ones were zeros. Or I could actually do synthetic division at this point. Since 1 is a 0, I could actually plug in 1. Now keep in mind, I'm actually plugging in the number 1 because this would be written as x minus 1 into the factored form. So I am actually plugging in the value 1, not -1, because 1 is the actual 0. So I'm going to go straight down. 1 times 2 is 2. 5 times 1 is 5. -3. -3 times 1 is -3. So this is what I have left after I have that 1 gone. 2x squared plus 5x minus 3. And I could multiply x squared plus 5x minus 6, which gives me x minus 3. Nope. This one we want the -6 and a +5. So x minus 1 and x plus 6 will multiply to get us -6 and add to give us 5. And then this would be 1 and -6 there. Oh no, this is bad, guys. I forgot to do what you're supposed to do. Watch yourself because it's really easy to do. We forgot to divide by 2 there. I was like, that doesn't make any sense. 6 wasn't a possible choice. But we forgot to divide by 2, people. We multiplied this 2 here. So this would be 2x minus 1 and x plus 3. So our zeros would be 1/2 and negative 3. So we found all of our zeros. And so this one just said find the rational zeros. We found them. 1/2, negative 3, and 1. So we could also do this by plugging in the values too. If you weren't able to go through the synthetic division, you can do your rational zero test and then plug them in to see which ones equal 0. Thanks, guys.